안녕하세요 여러분, 혜리입니다. So in this video we're going to finish the HO syllabus for vectors. So in the last video for SL syllabus, we have seen one of the form of equation of a line. So a line in a vector form, right? So let's quickly recap that. So we have a form like this, right? So lambda is any real number, so lambda is a constant. So R here tells you the position of the point of the line. So A is any point or a position vector on that line. So okay, not position vector on the line, but any point on that line. So A refers to the position vector of the certain point, and D here is the direction vector, right? Then we can try to write this like this. So again, this R shows the position of all the points on that line. So we can write it as x, y, z. And so any point, let's say the point is a1, a2, a3, and the direction vector as d1, d2, d3. Then we have this equation, right? And we can see that the vector are identical when the components are the same, right? So in that means this x here, we can write it as a1 plus lambda d1, right? And this y here, we can write it as a2 plus lambda d2, and z here, we can write it as a3 plus lambda d3. And again, lambda is a real number, and we call this as a parametric form. Parametric form of a line. Okay, so here lambda is the parameter. Okay, and let's try to rewrite this a bit more, so that for the first equation, let's try to write lambda in terms of x. So here we move a1, right? So x minus a1, and then divide it by d1. Then we have lambda equals to x minus a1 over d1. And similarly, we can also write lambda in terms of y. So lambda as y minus a2 over d2. And lastly, for this one, lambda as z minus a3 over d3. And here, these lambdas should be the same, right? So that means x minus a1 over d1 must equal to y minus a2 over d2, and it must equal to z minus a3 over d3. And this, we call it as Cartesian form. So Cartesian form of a line, okay? Then some may wonder, so it's absolutely fine to have some of the components as 0 for the direction vector. So for example, let's say d3 equals to 0. So like let's say 1, 2, 0 like this, okay? Then we can see that we have a 0 in the denominator, right? And we clearly know that that's violating the mathematical equation because that's undefined. Then how can we do that? So this Cartesian form, where is it from? It's from the parametric form, right? So when d3 equals to 0, that means z equals to a3 because d3 is 0, right? So we don't have this term, so we will have z equals to a3. So don't worry, if we have d3 equals to 0, then that means it's just this. So what it means by d3 equals to 0 is that the z value doesn't change. So it's always constant, okay? And that's it. So these are the forms of lines in vectors that we have to know. And let's try some examples. So for vectors, there are a lot of varieties of questions. So I have prepared a lot more examples than the other chapters. So let's try them. So find the equation of the line in Cartesian form which passes 1, -2, 3 and is parallel to alright, so it's parallel to this line, okay? So we want to find the Cartesian form of a line, right? And in order to find the equation of the line, no matter which form we want, what do we need? We need the point and the direction vector, right? Point and the direction vector, point and the direction vector. So we already have the point, right? Because the line we are looking for passes through this point. Then what about the direction vector? So in the question it says the line we're trying to find is parallel to this line, right? Then how do we find the direction vector of this line? So it seems like it's slightly different, right? So we should have denominators as direction vector, right? But instead we have as coefficients, not the denominator. So okay, not so on the numerator, right? Not in the denominator. Then what can we do? So we can either write this 3 as 1/3, 1/6, and 1/2. So call the direction vector as 1/3, 1/6, 1/2. But we can also divide this by the least common multiple. So for this case, the least common multiple of 3, 6, 2 is 6, right? So we can write that as this. So we have the direction vector of 2, 1, 3. So it's up to you which one to use, but certainly this will be better in terms of calculation, okay? Because we don't like having a lot of rational numbers in the arithmetic, okay? So we have the direction vector and we know the point, right? Then we can write the equation in Cartesian form. So x minus 1, right, over 2, y plus 2 over 1, and z minus 3 over 3. So that's the equation of the line, okay? So not that difficult. Alright, then let's move on to the other example. So a bit more difficult than the previous one. So let's say we have a point like this, and we have a line equation in Cartesian form again. And let's say if AD is perpendicular to this line, find the coordinate D. Alright, so maybe we can try to sketch a simple diagram, draw a simple diagram of this. So of course it's almost impossible to sketch this in scale, right? Because it's in 3D. So just make a line, right? And then the point A must be outside the line, right? Because you can quickly check. So 3, that means -3 times 3, so -9. And it's -1, so -8 times 2, which is -16. So it's not, this point does not lie on this line, okay? So this is what we have. And what we want to look for is the point D, where AD is perpendicular to line L, right? Okay, then that means we certainly need the direction vector of L, right? So we know that the angle between the two vectors are perpendicular at 90 degrees, right? And what does that tell us? That means the dot product of them is 0, because dot product we have cosine theta, right? And cosine 90 is 0. So we can try to apply what we learned from dot products or scalar products for this question. So let's try to find the equation of the direction vector of L first. So as what we did previously, we have all the numbers in the numerator. So in order to make the number in the denominator, we can try to divide everything by the least common multiple. So the least common multiple of 3 to 3 must be 6, right? So that means x minus 6 over 2, y minus 7 over 3, and z minus 5 over 2. So the direction vector of this line must be 2, 3, 2. Okay, so the direction vector of line is this. Then what about the direction vector of AD? So in order to find the direction vector, that means we need the two coordinates and then we can try to subtract it, right? So AD, we can find it by OD minus OA, and remember the position vector is the coordinate, so we can directly use that. Then that means we need the coordinate for D, right? But we don't know it. That's why we're trying to find it. So what can we do for D? So clearly we know that D lies on this line, right? Then if we change this into vector form, we will have 6, 7, 5 plus lambda 2, 3, 2, where lambda belongs to real number, and that will be the point, every point on this line. Then why don't we write D as 6 plus 2 lambda and 7 plus 3 lambda and 5 plus 2 lambda, right? And that means we know the coordinate for D, right? So that should be 6 plus 2 lambda, 7 plus 3 lambda, 5 plus 2 lambda, and we subtract it by the coordinate. So we will have 3 plus 2 lambda, 8 plus 3 lambda, and 2 plus 2 lambda. And that's the direction vector of AD. And we know that the dot product of AD and the direction vector of the line must be 0, because we don't need to know the magnitude. So remember, dot product, it's the magnitude of AD, magnitude of D times cosine theta, where the theta is the angle between them. And the angle between them is 90 degrees, so cosine 90 is 0. That's why we have this property. So their dot product must be 0, and there is another way of finding the dot product, right? Which is using the components, so component by component. So 3 plus 2 lambda, 8 plus 3 lambda, 2 plus 2 lambda, dot 2, 3, 2. So we have 6 plus 4 lambda plus 24 plus 9 lambda plus 4 plus 4 lambda equals to 0. And we can solve for lambda, which will be -2. Then we know the point for D, because the point of D is basically OD, the position vector, right? And the position of D is given like this. So that means D here is 6 plus 2 minus 2, 7 plus 3 minus 2, and 5 plus 2 minus 2, which is 6 minus, so 2, 1, and 1. And that's the position vector. So if we are asked to find the coordinate, then we can just write it like this, okay? So that's it, not that hard, right? So just apply what you know. And whenever you there's like angle involved, then most likely you'll have to use the dot product, okay? There's another thing that you can use called the cross product, which we are going to learn later. But yeah, you can, dot product is more applicable, okay? So let's see one last example, which is not that hard. It's basically almost the same example as this, but just in different wording. actually I'll just write it so right here as in the same paper so that it's gonna be easier for you to look at the notes. So example 3 here is again the same values, so same coordinate and same line, and we want to find the shortest distance from A to L. So shortest distance is always the perpendicular. It's always. And why? So you can try to use some of the triangles property. So let's say we have, let's say, yeah, I'll just use, sorry. So yeah, let's say we have L here and we have A here. So you can see that the distance from A to L there can be many answers like these, right? And just by looking at the sketch, you can see that this is the shortest. And why? Because this one is the shortest because the other lengths are always the hypotenuse. If you can sketch the right angle triangle, all the lengths here are all hypotenuse except for this. This is where it becomes the opposite, right? That's why this perpendicular line is the shortest. And if you want to find the shortest distance, that means you need to find the coordinate D, and then you just find the magnitude of AD. That's it, okay? So we have already calculated the value for D, right? So that means we just need the magnitude of AD. So AD here is this, right? So we just substitute lambda as -2. So that will be -1, 2, and -2. Then the magnitude of AD must be root -1 squared, which is 1, 2 squared, and -2 squared. So that will be 3. Okay? So this is an example of the different forms of line and some calculations with lines. Okay? So now what we are going to do is that we are going to learn another vector arithmetic. It's called the vector product, or it's also called as the cross product. So we have learned one of the multiplication of vector before, right? Called the scalar product, and as what the name says, it gives us the scalar, right? As the product, as the output, right? For this one, as what it says from the name, it gives us the vector after we multiply it, okay? So, like for example, if you have to find energy, which is a scalar quantity, then that means you have to use a scalar product. And for example, if you have to find force, for example, then force is a vector quantity. That means we may be able to use vector product, okay? But before we calculate those physics quantities, we first need to understand what vector product does, right? So let's see. Let's say a vector A has component A1, A2, A3, and vector B has component B1, B2, and B3, okay? Then A cross B, which is a cross product, is the determinant of 3 by 3 matrix when we apply something called the transpose onto these vectors. But you guys don't have to learn linear algebra, so you just need to know how to compute A cross B, okay? So the way we do it is, so look carefully, for the I component, we use AD's rectangle. So we multiply this and we subtract the product of these two. So the x component, which corresponds to I, remember the base vector form, so it becomes a2 times b3 minus a3 times b2. Then what about j? J uses these thing, but it's always from how should I say? It's always from right to left. So what it means is that we always look for we start from the right column on the right. Okay, so for I, we use the column on the right, right? For j, we have the column for right and left. Then that means this a1 and b1, we move it to here, and then do the same thing as what we did for I. So we have a3 b1 minus a1 b3. Okay, and lastly for k, you move a2 b2 here, but it's just the same as looking at this, right? So it's a1 b2 minus a2 b1. Okay, so that's certainly a component form of a vector. So we can see that the outcome of cross product is vector. Okay, and there is another way to find this, like what we did for dot products. So if we have a cross b, then we can write it as the magnitude of a times the magnitude of b times sine theta. So the theta is the angle between them, and we have a unit vector. But this unit vector is difficult to find. So usually we use this thing for finding the magnitude. Okay, so for example, if we have a cross b magnitude, so since a cross b is a vector, so it's absolutely fine to find the magnitude of the vector, right? So we can either try the root this thing squared plus this thing squared plus this thing squared, but we can also use this. So magnitude of this. Magnitude of magnitude is just still the magnitude, and it's the same for b, and it's just a modulus of psi. And what's the magnitude of a unit vector? As we learned, it must be 1. That's why we don't have it. So a cross b will have this value. Okay, and what does this mean? So if we have vector a and vector b like this, and if we have an angle here, then so this length here should be the magnitude of a, and the length here will be the magnitude of b, right? Then the area of a triangle as what we learned from the trigonometric chapter, we can find it by the two adjacent lengths with the angle between it. So it's half this length times this length times sine theta, right? Then what does it mean by this? So that. And note that if we look for the acute angle, then sine theta is always positive, and so it's absolutely fine to put this, okay? And what does it mean by if we don't have half? That means it's the area of a parallelogram, okay? So that one gives us the area of a parallelogram. Okay, so that means we can, by dividing this by half, we can find the area of a triangle. Okay, so this is the area of a triangle. So that's one of the aspects, geometrical meaning of a cross b. And there is something else that we need to know. So here we have seen the magnitude, right? So magnitude of A cross B gives us the area of the parallelogram formed by A and B, vector A and B. But what if without the magnitude? So just A cross B. What does that mean? So let's say we have a vector A and vector B. Then it must have an angle like this, right? And let's say there's a vector C like this. And C here is perpendicular to A and perpendicular to B. Then C is, we can find C by finding A cross B. Okay, so that means the cross product of the two vectors yields the direction vector of the normal vector that is both perpendicular to AB. And this, okay? So that's what it means. So that means by using the cross product, we can either apply this to find the area of a parallelogram or the triangle, so some of the like area of some shapes, or we can also find the normal vector, okay? So let's try some basic properties like what we did for scalar product. So basic properties. So if we have A cross B, then is that the same as B cross A? And the answer is no. So be careful. The commutative law it's not satisfied for cross product, and instead we have to put negative sign. Then how do we prove this? So let's say A is A1, A2, A3, and B is B1, B2, B3. So we have already computed A cross B for this case, right? We have this. So A2, B3 minus A3, B2. A3, B1 minus A1, B3. And A2, B1. Sorry, A1, B2. Minus A2, B1. Yeah, I didn't memorize it in this way. I always use the determinant of 3 by 3 matrix. So yeah, that one is, I think it's better to use the determinant form than just memorizing it, okay? Alright, so that's A cross B. Then let's check for B cross A. So B cross A is IJK. B first, so B1, B2, B3, and we have A1, A2, A3. So as what we did just now, so I, and then we look for the right side of the two column vector. So B2, A3 minus B3, A2. And for J, we use these two columns, but again, we look for the right first. So move this left column to the right. So we have B3A1 minus A3B1. And lastly, K, we move this there, but it's identical to C, just this, right? So B1A2 minus B2A1. Oh, I should have written, yeah, but anyway, so we have this, right? And how can we compare these two? So we can see that B2A3 is here, and B3A2 is here. So we can see that A cross B equals to negative B cross A. Okay? That's the first thing. Second thing is when we have a multiple, so a constant multiply, then we can just move it anywhere as what we did for a scale product. Okay? Scalar product. Lastly, then does the distributive law works? And the answer is yes, it does. So just be careful with the commutative law, okay? So we have some of this. Then let's, for example, let's see whether what happens if we have whether we can find this. So my first question is, can we have the answer for this? And without trying like this, can we find it? And the answer is no, and it's very easy to find. It's easy to know because what's the output of scalar product? Scalar, right? And what do we need in order to do vector product? We need two vectors. What does this mean? It means we are doing a cross product with a vector and a scalar, right? So that means this thing doesn't exist. Then what about this? Does it exist? For this one, yes it does, because A cross C is a vector, and scalar product of two vectors, that's absolutely fine, right? So we can see this. And very important fact you have to know is that A cross B cross, when you have three vectors to cross, this is not the same as this. In order to prove this, you can try to use this, but it's gonna be very difficult. So I would recommend you to try using this. So for example, A cross, so if we have A here and then B here, let's say, then so that it doesn't necessarily mean that they should lie on like the same plane, but let's say we have like a like ABC like this, okay? I'm running out of pen, but anyway, so A cross B must have a vector that is both perpendicular to these two, right? So we have, let's say we have like a vector like this. So, okay, it's, yeah, so, okay, we have a vector like this, okay? Then, the cross product of this vector and this vector should be a vector like my phone, right? Okay, it's very hard to show, like using, I don't have enough pens to show, but yeah, you guys can try to think using this idea to see, okay? Or if that's too hard, then unfortunately you have to do this, but it's gonna be very time consuming. So you don't really need to know the proof, I guess, but yeah, it's good to know to verify whether this is true or not by yourself, okay? So please have a try. And let's try another example of using 3D. So with cross product, vector product, you have a lot of questions involving 3D shapes. So the ones that we are going to learn very soon, planes. So let's say we have a tetrahedron with a vector A here, vector B, and vector C. C as this vector, okay? A, B, and C, okay? And show that the volume of this tetrahedron can be written like this. Oops, so this must be bracket, because note that if it's modulus, that means we're just doing a scalar product of a scalar with vector, right? Which doesn't make sense. So yeah, bracket, okay? So let's try to show this. How do we find the volume of a tetrahedron? So you should know that volume of a tetrahedron is 1/3 times the base area times the height. Okay? So that means we need a height like this, that's which is perpendicular to the base. So how do we find the base area? So base is a triangle with vector A and B like this, right? So as what we learned from cross product, the area of the triangle here is just half A cross B, right? Certainly, right? Then what about the height? So the height here is perpendicular to this plane, right? And also we can note that, so if we have to find the angle between C and the plane, we need the perpendicular line, like what we did for 3D in trigonometry. So if you look at this triangle, so that's C, that's the height, that's that's the angle. So this is the angle, let's say. So that's this adjacent is the plane. So the base, from the base, okay? This length. How do we find height? The length of this hypotenuse is the magnitude of C, right? That means cosine theta equals to h over magnitude of C. That means h equals to magnitude of C times cosine theta. So volume would be 1/3 times half times magnitude of A cross B times magnitude of C times cosine theta. And what is this theta? The angle here is the angle between C and the base plane, right? That means we can have this as 1/6 A cross B dot C. So consider A cross B as a vector, okay? So remember that if you have A dot B, then we have magnitude of A times magnitude of B times cosine theta, where the theta, the angle, is the angle between A and B, right? Just imagine that we have a vector of A cross B. So A cross B certainly gives us the vector, right? Gives us a vector. So vector magnitude times angle, cosine angle, and this angle is in fact the angle between these two vectors, right? Plane C, right? So why can't we just treat A cross B as just a single vector? Then we will have this, right? So that's why we can find the volume of tetrahedron like this. Okay, so that's it. Very simple. But for some cases, you may have a negative value for this, for an obtuse angle. So obtuse angle, as it means that it's something like so A, B, and C, something like this. Okay, it's a bit hard to sketch. I didn't really mean this, but yeah, so you may have an obtuse angle. In that case, it's negative. Then you know that volume is always positive, right? So just put the modulus sign and that should be fine, okay? So that's how we can find the volume of a tetrahedron. So that's another example of the cross product using some of the by combining with the dot product. And now we are going to move to planes. And this is where the IV vector gets, how should I say, more interesting, I'd say. So for lines, we had many forms, right? So we had a vector form. So for example, we have a component form, base vector form, and for line, we have a vector form and what is it? Cartesian form, parametric form, right? For plane, we also have a vector form. And for the derivation, I'm not going to talk about it because it's a bit hard to sketch. So we have R here, which refers to any point on the plane, and it's very similar to the line. So this this A here is a specific point on a plane, and this D1 is a direction vector, and this D2 is also direction vector, and these two vectors, so the plane must be parallel to these two. So you can just think that the plane contains these two direction vectors, okay? So then let's try an example. So find the equation of a plane in containing point A as 1 to -3, B as -1 to -2, and C as -3, 1, 0 in this form. Oh, and one more thing. So as what we had for the equation of line, lambda and mu must be real number. Okay, so basically we have a plane. We want to find a plane in a vector form where it contains the point A, B, and C, right? So then we have a lot of points, right? So we can use any. We can either use this or this or this, okay? So it's fine about the point. Then what do we need? We need two direction vectors, right? And how do we find the direction vector? So we just need any two direction vector. Then why don't we just use AB and BC? So AB here is OB minus OA, right? So that means subtracting this by this. So we will have -2 and then so 0 and 1, right? So BC here is OC minus OB, right? So we will have -2, -1, and 2. Alright? Then we're done. The equation of the plane, I'll use A. So 1 to -3 plus lambda -2, 0, 1 plus mu -2, -1, 2. And so lambda and mu are real number. That's it. So very simple, right? So that's the vector form of a plane. What's next? We have another form called the scalar product form. So as what it says, scalar product, you will have a scalar product involved. So we have the position of any point on the plane dot a vector called n. So this is the scalar product form of a vector. And what is this n? This n is a normal vector. That means a vector perpendicular to the plane. And are they the same plane? Same vector? Yes, they are. So these two are the same vector. Then what's A? A is just a point on a plane. Why do we have a normal vector? Because the thing that determines a unique plane is the normal vector. Why? So imagine you have a plane like this. There are so many direction vectors which are parallel to this plane. That's why we needed two parallel planes. Two direction vectors that are both parallel to plane. Okay? And the reason why we need these two, we can find it from here. I'll tell you very quickly. So if we have a plane, then we certainly have a normal vector, and the direction vector of this normal vector is unique. Okay, so it can be like negative here, like this, but it's the same. The direction must be the same. It's just by -1. Okay, so only the normal vector determines the unique plane. And why do we need two direction vectors? Because that's what we did for cross product. If we have two vectors, then we can find a normal vector that is both perpendicular to this and that, right? And the plane parallel to these two, that means the plane contains these two vectors, right? So we have a plane with D1 and D2. And imagine that if we cross D1 and D2, we will have a perpendicular vector which is also normal to the plane. That's why we need two direction vectors here. And for here, this is how we can determine a unique plane. So like what we had for line, if we have to find a unique line, we need a point and a direction vector, right? For plane, we need a point and a normal vector, okay? Then from this, so R, as I said, it's the position of every point, right, on the plane. So we can write it as x, y, z, right? Dot. Let's say the normal vector is a, b, c. Okay, and let's say this a vector is a1, a2, a3, and we dot with a, b, c, the normal vector. So here n is a, b, c, and a is a1, a2, a3. Okay, then we can expand this out, right? We know how to do scalar products. So we have ax plus by plus cz, and we will have a constant here, so let's just call it as d. Then this is called the Cartesian form. Oops, I shouldn't have, okay, Cartesian form. Okay, so you need to know three different forms of plane. So vector form like this, and scalar form like this, and Cartesian form like this. Okay, then like what we did for line, let's try some examples. So remember the example that we have just seen, this example. We want, now what we're going to do is that we're going to write this in Cartesian form. Okay, so in order to find the Cartesian form, what do we need? We need a point and a normal vector, right? So we have plenty of points, right? So just quickly writing the points out. So yeah, we can use any point here. So point should be fine. That means we have to find the normal vector, right? And in order to find the normal vector, we need two vectors on the any vectors on the line, on the plane, Then some may ask, can't we just use the position vector of a, b, and c? The answer is no, because we cannot guarantee that the origin lies on the plane. So for example, let's say the origin is here, and we have a plane like this. So we see that the origin is not on the plane, and let's say we have a, b, and c. Then the position vector of a is this, and OB is this, and c is this. Are any of these parallel to this plane? The answer is no. That's why we cannot use the point, the position vector, right? So we have to use this either AB or BC or AC, okay? Because we can clearly see that this AB or BC or AC, they are on the plane, okay? So we are going to use the two direction vectors that we have found. So we are going to use AB, which is -2, 0, 1, and BC, which is -2, -1, and 2. Yeah, so we're going to use these two. So in order to find the normal vector, that means the cross product of AB and BC. Okay, then again the determinant of 3 by 3 matrix. So we will have this minus this, so that's 1, and move negative 2 here. So this minus that, so we have 2, negative 2 plus 4, right? And lastly, 2 minus 0, so we have this as the normal vector. Then some may also ask, why can we use BC cross AB? We can use that absolutely fine. It's just that we will have negative value, right? Then clearly the two normal vectors are not identical, right? Then which one, can we use them both? Yes, we can. Because why? Remember that if we have to find this into Cartesian form, we have to dot the normal vector with the position of any point on the plane and a specific point, right? Imagine we use BC cross AB. That means we have minus here, right? And due to the equality sign here, the minus can cancel out. So it does not affect the result, okay? So the order for, of course, if we switch the order, they will give you the different vector. But for this particular plane case, where we can cancel the negative sign, it does not affect, okay? So we can use anything. So Cartesian form, that means x plus 2y plus 2z. And this one is 1 plus 4 minus 6, so which is negative 1. So we move it to one side, usually, okay? So we have plus 1 equals to 0. And that's the Cartesian form of the plane, okay? So not that difficult, right? So let's try another example. So again, find the equation of the plane that passes 2, negative 4, and 3, and is parallel to another plane, 2x plus 3y minus 5z plus 1 equals to 0. Oh, in the Cartesian form. Alright, so again, in order to find the equation of the plane, what do we need? Equation of the plane in Cartesian form, what do we need? We need a point and a normal vector. So the point is already provided, so we don't have to worry about that. The thing we have to worry about is the normal vector. So we have a plane, we are given with a plane, right? So if a plane is parallel to another plane, like this, then what do you think the normal vector would look like? They will share the same normal vector, right? Parallel, that means they have the same normal vector. Then what's the normal vector of this plane? It's the coefficient of x, y, z, right? So the normal vector here is just 2, 3, negative 5. And we're done. X, y, z dot 2, 3, negative 5 equals to 2, negative 4, 3 dot 2, 3, negative 5. And note that in order to find the Cartesian form, we need to write it in scalar product form first. And then the expansion of the scalar product form will be the Cartesian form. So we will have 2x plus 3y minus 5z equals to 4 minus 12 minus 15. So that's negative 27, so that's negative 23. So 2x plus 3y minus 5z plus 23 equals to 0. And that's the Cartesian form of the plane. Okay? So not that difficult, right? Now, one last example. But this so I'm trying various types of examples so that you guys can handle many other like different kinds of questions, okay? So again, find the equation of a plane that passes through the point P102 and contains a line this, okay? So and if we ask you to find the equation of a plane, that means a Cartesian form, okay? So basically we have to find the Cartesian form of the plane. So again, in order to find the Cartesian form, that means we will have to write the vector the plane in scalar product form first, right? And in order to expand that, we need the normal vector and the point. So again, the point is already provided, so we don't really have to worry about that. But what about the normal vector? Unlike the previous cases, we only have a line, just one line, right? Then so clearly we can use the direction vector of this line, right? As it's on the plane, the line is on the plane. But what about the other direction vector? Remember, in order to find the normal vector, we need two vectors on the plane so that we can do the cross product. But we only have one. Then what can we do? So let's try to sketch this. So we're trying to find a plane that contains this line L and also contains the point P, right? Then we have a direction vector of this L, right? And certainly we will have a certain point on this line L too, right? Then can't we just use this direction vector as well? Because certainly these two are the different direction vectors, right? Then we just need any point on line L, right? So line L, so it's in Cartesian form, but let's try to change this into vector form, which is more familiar to most of you guys. So this is the vector form. That means this line has a point 3, 4, 2. So let's call this point as 3, 4, 2 then. Then that means we can use this AP or PA, doesn't really matter. So let's try to use the let's try to find the vector, this AP. So that's OP minus OA. So P here, we already know it. 1, 0, 2. And we subtract 3, 4, 2. So we can find AP like this, right? Then we can do this cross product. So we know the direction vector of L as 1, 3, negative 2, right? And we have another direction vector, negative 2, negative 4, and 0. So that means the cross product, so let's call, the cross product of AP, and let's call this as D, is, again, the determinant of 3 by 3 matrix. So we have 8 minus 0, so it's just 8, and then we move negative 2 and 1. So 0 minus 4, and negative 6 plus 4, right? Negative 6 plus 4, so that's negative 2. Okay, so 8, negative 4, and negative 2. And we see that we have a common factor here too, right? Then can we just divide this by common factor? Note that if we just, so it's not just, you can't write it like this, okay? No, because they have different magnitude, right? So they're different vectors. But for normal vector, we can use this so that we will have smaller numbers, and we always prefer smaller numbers, right? And why can we use this? Because remember the scalar product form? So we have to, so let's use this first. So that means we have to use, so let's say I'm gonna use point P. We can use A, but yeah, I'm going to use P here. So we have this, okay? And you see that if we take the common factor 2 out, then you see that we can cancel it due to the equality. That's why we can use this, okay? But note that these two are different vectors because they have different magnitude, right? So we can use the smaller numbers. So So that means we have 4x minus 2y minus z equals to 4 minus 2. So we have 4x minus 2y minus z minus 2 equals to 0. Okay? So that's how we can find the equation of the plane for this question. So we're almost done. Now what we're going to do is some applications of plane and lines now. So angle between plane and line. So this will be the first thing that we're going to see. Or plane and plane. So this will be the second thing that we're going to see. So line and line we have already said it using the dot product, right? And we're going to see for plane and line. So the first case. So please note that although it's not possible to sketch a perfect diagram on scale, we can still draw a rough sketch to understand the question. So angle between plane and line. So that means we have a line, we have a plane here, and we will have a line, and as it says it has an angle, that means they must intersect, right? And the angle here should be this angle, right? Then in order to find this angle, then you may think that, so we will have the direction vector of L, so that should be fine, but we need to find the direction vector or any vector on this plane. And if you think like that, you'll have wrong answer, because we need this particular direction vector. For example, if we have this, so this direction vector is on the plane, right? So this is also another direction vector of this plane, but can we use this to find the angle? The answer is no, right? So then using the direction vector on the plane seems like it's very difficult, because we need a particular one direction vector out of infinitely many direction vectors on the plane. Then is there anything that we can use as a unique vector? There is. What is it? It's a normal vector of a plane, because as what we have discussed before, if we have a plane, then there must be a unique normal vector. In other words, normal vector is the one that determines a unique plane. So, and also a point, but here we need the normal vector. So yeah, so that means we can use the normal vector to find this angle first, and in order to find theta, so theta is the angle between plane and line. This angle is the angle between the line and the normal vector. So we have to subtract this phi from 90 degree. Okay, so then let's try an example like find the acute angle formed by line and plane So we usually use this pi as a variable to indicate the equation of a plane, okay? So this is the question, okay? Alright, then, as I said, we can't draw a perfect diagram, but let's try to sketch a rough diagram to understand the question. So that's the plane pi 1, right? And there's a line L1 intersecting this plane, and we want to find this angle. And again, it's almost impossible to find this specific direction vector, so we're going to use the normal vector. And what's the normal vector of pi 1? It's the coefficient, right? So it's 4, minus 5, and negative 3, right? 4, minus 5, minus 3. Okay? Then what about the direction vector of L1? So we have again, we have 20, -12, and 15 as in a numerator. So we divide them by the least common multiple, and seems like it's 360, is it? Oh, sorry, yeah, 60. So we divide that by 60. That means this. So that means the direction vector here is 3, -5, and 4, right? So that means we can try to find the angle between this normal vector and the line direction vector of L1. How? By using the dot product, right? So the dot product of the normal vector and the direction vector. So here we know that it's component by component, right? So 9 plus 25 minus 12. Okay, and it's also equivalent to the magnitude of normal vector times the magnitude of the direction vector times the angle between them, right? And so that means, so that one we have 22. The magnitude of the normal vector is root 16 plus 25 plus 9, and the magnitude of the direction vector is 9 plus 25 plus 16, so they're the same, right? So cosine theta equals to 22 over 50. Okay, seems like I have done something wrong. Oh, sorry, so it's not 9, it should be 12, right? 12, 25, and -12. So yeah, that should be 25. So it's half. Yeah, I made a question to have a special angle. I don't want to use calculator. So yeah, anyway, here theta here is, so cosine theta equals to half. What is it? Or 60 degree. So note that you have to calculate it very quickly, okay? So, oh, sorry. So this theta here is not this theta. So, okay, I'll not use this theta, sorry. So it should be phi. So just phi, not phi. So that's the angle of phi. That means theta equals to 90 minus 60 degrees, so it should be 30 degrees. Okay, so that's one of the application. Now we want to find plane and plane. Okay, and also this one, it's not going to be easy to sketch, right? But just try to make a rough sketch, like this. Okay, so we want to find the angle between these two planes, and note that again, so we can still try to use the direction vector like this, but it's gonna be very difficult, right? It's very hard to find this unique direction vector. So what we can do is that we can use the normal vector, right? So there must be a normal vector here, and there must be a normal vector of this plane, red plane too, right? Then what does this diagram show you? So we can see that the normal vector and the normal vector they form a shape like this, four-sided shape, right? Then which angle are we trying to find? So angle between two planes, so that means this, right? So we can find this. And what's the angle here? How do we find this angle? So let's call it as phi. how do we find this angle? We just need to do the dot product of the two normal vectors, right? And that means phi plus theta equals to 180, right? So we can clearly find this. So then let's try an example. So find the acute angle formed by plane 3x minus 2y minus z plus 4 equals to 0, and plane 2, 2x plus y minus 3z plus 2 equals to 0. So the normal vector of the first plane should be 3, negative 2, and negative 1, right? So the coefficient of x, y, z. And the normal vector of the plane 2 will be 2, 1, and negative 3. So we have the two normal vectors, and then that means we can find phi very easily, right? So n1 dot n2, that means 3 times 2, so 6 minus 2 plus 3, right? So that's 7. And we can also find this by using the magnitude with the angle, right? So the magnitude of n1, that means root 9 plus 4 plus 1, and the magnitude of n2 is 4 plus 1 plus 9, so we can see that they're the same. So we have 14 cosine phi equals to 7. So cosine phi equals to half, right? That means phi equals to 30 degree. Oh, sorry, 60 degree, 60 degree. Okay? That means theta is 180 minus phi, right? And that means 120 degree, right? Then what does this, then is this an acute angle? No, right? Then did we do something wrong? No, we did the correct thing. We just need to find this angle, the acute angle. Okay, so the answer must be 60 degree. Okay, so that's it. Very, very simple, right? After this is what you have to do is that you have to be able to find the intersections. So for example, intersection of three planes, or intersecting line of three planes, or show that a plane does not have an intersection. And you should have done this already in systems of equations, where you have three equations with three variables, and you have learned how to find a unique solution, or no solution, or infinitely many solution, right? So all right, I'll just quickly tell you about that. So finding the intersection of planes. So it's very hard to sketch for me, to be honest. I'm not a person who can sketch nicely. So unique solution of three equations in the systems of equations, that means it's equivalent to say that a plane has an intersection, so one intersection. Okay, so no, not all. So three planes have an intersection. Okay, what about when it means infinitely many solutions? That means three planes have an intersecting line. So that means something like, so I'm very bad at sketching, so I don't know whether you guys can understand this diagram. So this is what it means. So you see that this line, so every plane contains this line. So this is where we have infinitely many solutions. And lastly, no solution. That means 3 planes do not have an intersection. So you can try to recall the skew lines. So you'll have a plane like intersecting 2 by 2 but not 3 at the same time, like this. And I have a very poor sketch. So yeah, this is something like this. So you can see that there is intersection among pair of planes, so like this, but there's no the intersecting point for the 3 planes. Okay, so I assume that you have already done this a lot for systems of equations, and usually you will use a calculator to solve it. You can use Gaussian elimination, but these questions are asked in paper 2 a lot. For paper 1, if you have a paper 1, unfortunately you will have to use Gaussian elimination. And actually you can use the properties of linear algebra, so the matrices, but that's gonna be too much for you, so I'm not going to talk about this any further. Okay, and also we will have much more varieties of questions. So for example, this distance between skew lines, or distance between a point and a plane, etc. And so there are too many examples that we have to talk about, and you can see that the video is already almost like 90 minutes. So I'm going to put all those kinds of questions in the sample test, so please have a try of the sample test. Okay, so that's it for IB vector, and please IBHO vector, and please be reminded that again, all the questions we have done so far are probably the easiest. Okay, so you really have to try the sample test and some past papers to get more experience with harder questions. Okay, so the difficulties of your final exam or mock exams will be much harder than these. So please have a try on the sample test. Okay, that's it for today. So see you guys in the next video. Bye.